In the last lecture, we talked about a method to find out a starting basic feasible solution for a linear programming problem. When problems are large, you cannot always find a starting basic feasible solution by inspection. So, I gave you phase 1 and phase 2, phase 1 and phase 2 method. So, essentially phase 1 did the job of finding a feasible solution if there was one basic feasible solution, or it told you that there was no basic feasible solution to the system and hence the problem was infeasible. So, once phase 1 was over and you found a basic feasible solution, then we went on to phase 2 to get an optimal linear programming solution, optimal basic feasible solution. I will give you another alternate method when you do not have starting feasible solution right away, and so that is known as the. So, I am going to talk about BigM method. Here also we make use of artificial variables, and let us see how the method works. So, if you have a linear programming problem given by this, you have plus x4, then you have minus x5 minus x6. So, therefore, a starting feasible solution is not right away available, right. So, we will use the trick of again adding artificial variables essentially to the second and the third constraint, because I already have a unit vector here, and you see because we the idea is that we want to have a starting basis as an identity matrix, because then you do not have to do the calculations right in the beginning, and later on you can of course by updating or pivoting you can keep getting the new quantities that you need. So, here therefore, I will add the artificial variables, and I will come back to the objective function. So, this will be x1 plus x2 plus 2x3 plus x4 is equal to 4. This constraint remains unaltered. Then minus x1 plus x3 minus x5 plus xa1. So, this I will add an artificial variable here to start off. Then the third constraint is x3 minus x6 plus xa2 is equal to 3, and all the variables xj's are greater than 0 for all j, and xa1 xa2 are greater than or equal to 0. Okay. Then what I have done here is added the cost coefficient of the artificial variables as m. So, this is a very large number. So, let me say here, that is why we call BigM method. M is a very large number. The idea is that in case there is a feasible solution to the original problem, then because these cost coefficients are very large and you are minimizing, so therefore, m is a very large positive number, I should say. Yeah, that is very important, plus number, positive number. So, so therefore, if there is a feasible solution, then since the linear programming problem always goes to a better solution, there will be no incentive for the algorithm to select xa1, xa2 as a basic variable. Initially, of course, I am starting with the basis which consists of x4, xa1 and xa2 as the basic variables, but later on, because the process of simplest algorithm improves the value of the objective function at each iteration, or at least does not make it worse. It may remain the same in case of degeneracy, but otherwise it improves the value. So, hopefully, if there is a feasible solution to the original problem, these artificial variables should be driven out of the basis, right. So, let us see, we will start the algorithm here. So, quickly x1, x2, x3, x4, x5, x6, xa1, xa2, right, and this is your right hand side. So, then the objective function, this thing is minus 1, minus 3, 1, 0, 0, 0. This is m, m, and here right now this is 0. Okay, I am writing this as a constraint. Then 1, 1, 2, 1, 1, 1, 2, 1, 0, 0, 1, 0, 0, 0, and this is 4. Yes, I am trying to solve as many problems as possible so that you get very familiar with the simplex algorithm. Fine. So, second constraint will be -1 0 1, -1 0 1, then 0 -1, 0 -1, and then you have this 0 1 0, and this is also 4, right. And the last constraint is 0 0 1, and then you have 0 0 -1 0 1, and this is 3. Okay. So, this is your starting tableau, but it is not actually your starting tableau, because my basis consists of your basis B consists of the columns A4, AA1, AA2, right. So, I need to make these two coefficients here zeros, so that my top row will tell me the Cj minus Zj corresponding to this basis. So, multiply this row by m, this row by m, and subtract, right. So, I will make that computation right here, because we are not doing any other. So, m times you are adding, so this becomes m, right, and this does not change. Then 2m, so 1 minus 2m, right, this does not change, this becomes plus m. So, let me rewrite it here, plus m, right, this also becomes plus m, and these two become 0, and then this is 7 4m plus 3m, so minus 7m. So, right now the objective function value is very high, and this is your starting tableau. Since m is very large, this is the first negative entry in your Cj minus Zj row, and so I will make x3 a basic variable. We pivot. So, here this is 4 by 2, 4 by 1, and 3 by 1. So, no tie in the minimum ratio. This will be my variable to the variable to leave the basis will be x4. Okay. So, since the table is large, I will try to make the computations right here. So, this becomes 1 by 2, 1 by 2, this is 1, 1 by 2, and this is 2, right. Then the idea is that you have to actually multiply this by 1 minus 2m and then subtract. Okay. So, let us quickly do it. Yeah, it is going to take a lot of time, but so essentially you are multiplying this row by 2m minus 1. You are multiplying this by 2m minus 1 and adding. So, what will this coefficient be? I will do the computations here. So, this is m minus 1 plus half times 2m minus 1. So, this becomes m minus 1 plus m minus half. So, 2m minus 3 by 2. 2m minus 3 by 2. Then this is also the same thing. You have this and minus 3. So, here this is minus 3. So, m and so this will be m minus, yes, minus 7 by 2. Fine. This becomes 0. And this is again m minus half. Right. Yes, because 2m minus 1, I am taking the minus of that, right. Then this does not change, this does not change, nothing changes here. Your objective function value becomes minus 7m plus, see, remember we multiplied this by 2m minus 1, so 4m minus 2. So, the value is now minus 3m minus 2, minus 3m minus 2. So, the value has improved, right. Okay. Then you want to make zeros here quickly. So, just subtract this from here. So, this becomes plus half, this is minus half, 0, minus half, and then this is 2. Okay. You must keep checking that your if your pivot choice is right, then this side should always remain non-negative, because you are going from one basic feasible solution to another, right. Now, again I subtract this row from here. So, this becomes minus 1 by 2, minus 1 by 2, 0, minus 1 by 2, nothing changes here, this becomes 1. So, this is your new basic feasible solution. Your new basis is B now is consisting of A3, AA1, AA2, right. Okay. This is your new basis, and look at the optimality criteria. Okay, everything is, oh, so why is it, have we, right. So, M is a very large number, and you see that optimality criteria is satisfied. So, optimality criteria is satisfied. We cannot proceed with the simplex algorithm, but the value of the objective function, your artificial variables are in the basis. Therefore, since artificial variables are in the basis at positive level, so this implies problem is infeasible. Right. As I told you in the beginning, I will repeat it again, that in case there was a basic feasible solution to the original problem, the artificial variables would have been driven out. They would have become to 0 level. So, this tells you that the problem, starting problem, is infeasible. So, there is no point going ahead with it. Right. Now, I want to show you another case that can happen. Yeah, and in the meantime, try to think if there is any disadvantage of using these big numbers, because M has to be quite large. Here, of course, I cannot take examples to, but see, depending on how large your M is, how large your other numbers are, correspondingly your this thing will be there. So, M has to be correspondingly larger. Yeah, let me take another example for you. See, consider the final tableau of some LPP. So, final tableau I am talking for the BigM method, right. Suppose it shows you x1, x2, x3, x4, then xa1, xa2, right hand side. Okay. Now, the top row is 0, minus 2, 0, minus 1, m plus 2, m plus 1, 3. Okay. Then it is 1, 0, minus 1, 0, 0, 1, minus 1, minus 1, 2, 1, 1, 1, right, and this is 3, 2. So, you see the final tableau shows you that optimality criteria is not satisfied, but artificial variables are at 0 level. Your basis consists of basic variables are x1 and x3, right. Basic variables are x1 and x3. x1 is at level 3, x3 is at level 2, and this is a candidate for entering the basis because the corresponding Cj minus Zj is negative, but we see that all entries here are less than or equal to 0. Therefore, unboundedness criteria holds. Okay. And since the artificial variables are out of the basis, the original problem is unbounded, right. So, everything applies in the same way. Yeah, here also, yeah. So, here we could detect infeasibility, here we can detect unboundedness, right. Now, if artificial variables were in the basis at positive level and you had the unboundedness criteria, then you would conclude that the problem is infeasible, right. In this case, the problem is unbounded because the artificial variables are not in the basis. But in case, see, even though you have positive coefficients for artificial variables and whatever the number of artificial variables, even though the unboundedness criteria can still hold. Yes, you may detect the unboundedness criteria when the artificial variables are in the basis, because the other variables can take very large values and therefore go beyond the m values. So you can encounter unboundedness criteria in BigM method with artificial variables being in the basis at positive level. In that case, you will conclude that your problem is infeasible. But if you encounter the unboundedness criteria and the artificial variables are out of the basis, then you will say that the problem, original problem, is unbounded. Right? And in this case, of course, you come to the optimal solution with artificial variables being in the basis, then you conclude that the problem is infeasible. So that takes, so this, now the only disadvantage, as I told you to think about it, is that m has to be chosen very, very large compared to the other numbers, so that you don't ever mistake the sign of the Cj minus Zj number and so on. Because if these numbers, for example here, if this number or this number is very large, then m has to be correspondingly large, so that no, here you are saying that this Cj minus Zj is non-negative, is positive. So it should not happen that if you choose m, if you don't choose m sufficiently large, this number may be big, and so you will say that the optimality, the Cj minus Zj is negative, whereas actually it is required to be positive. So all these problems are there, and so when you have one single entry, to start off, when you have few entries which are very large compared to the other data, then computations of error or errors of computation can come in. So one has to be careful, and therefore mostly, as I told you, the computer programs are written for phase 1, phase 2. We seldom use, but sometimes this can be a good device to take care of, because certainly this does the job in one phase, whereas phase 1, phase 2, you often first obtain a starting feasible solution and then you start optimizing. So that is the thing, right? Okay. So that takes care of your this thing. Now we want to look at some other geometrical aspects of the simplex algorithm that makes it, you can visualize what is actually happening. So to do that, I'll first give you a graphical method of looking at the algorithm. Yeah, so graphical solutions I would like to give you, and let me consider. So we can, of course, I can draw it for you in 2 dimensions. So it's a small problem. Suppose, and I'm choosing just for a change a maximization problem instead of minimization. So this is 5x1 plus 4x2 subject to x1 plus 2x2 less than or equal to 6 minus 2x1 plus x2 less than or equal to 4, 5x1 plus 3x2 less than or equal to 15, x1, x2 greater than or equal to 0. Okay. So let's draw it. We can actually draw the feasible region in a plane, right? And I'll treat this as an equality first. So when you take it equal to 6, when you put x2 equal to 0, x1 has to take the value 6. So 1, 2, 3, 4, 5, 6. This is 1 point. When I put x1 equal to 0, x2 is equal to 3. So 1, 2, and 3. So this is the thing, and this side is the feasible region because 0 is on this side, less than, right? Now for this one, when you put x2 equal to 0, this gives you x1 equal to minus 2. So this is another 1 point. When you put this equal to 0, x2 equal to 4. So this is the thing, right? And here again, this is this side. And the third constraint, when you put this equal to 0, x1 is 3. And when you put x1 equal to 0, x2 is going to be 5. Right. So you see, and x1, x2 non-negative. So your feasible region is actually this. Right. This is your feasible region. We can quickly route out the extreme points here. This is 0, 0. This is 1, 2, 3, 3, 0. And this point is 0, 3. Right. And the point intersection. So you see that this constraint, which was your second constraint, minus 2x1 plus x2 less than or equal to 4, is actually redundant. It does not play a role in defining your feasible region, right? Because it's outside your feasible region. And this particular point I found out is 12 by 7 and 15 by 7. So just solve the two. Solve the two equations, this and this, and the intersecting point is this, right? Now just see the value of the objective function at the point 3, 0, for example. At 3, 0, your z is equal to what? 15. Okay. And at 0, 3, your z is 12. So, and of course at 0 it is 0, right? At 0. So the value is increasing in this direction. That means something like this, and then I'm not right. So this line will pass through this. So this corresponds to 12, and this corresponds to 15. So the value is actually increasing. So you see that it will, when it hits this point, 12 by 7 and 15 by 7. So let us compute at 12 by 7, 15 by 7, your value of z is equal to 12, 5 is 60 by 7 plus 60 again by 7. So this is 120 by 7, which is 7 ones are 7, 7, 7, and 1 by 7. So which is more than 50. Right. So the value of the objective function is actually increasing in this direction, and when it hits the point this, okay, the drawing is not very clear, but anyway you can see that this plane is moving parallelly to itself, and at this point it will be the maximum point. Right. So the value of the, so this is the whole idea, that in the simplex algorithm, see actually what we will see is that if you start with this as a feasible solution, then it will either move here or here, because we are following Bland's rule. So it's not necessary that it moves here, it may move here, and then from there it will come to this extreme point. So this is what will happen. Okay. So the simplex algorithm, when you start, because see this is redundant, it will come out to be, so anyway you will start with x3, x4 and x5, you will add the slack variables, all these are non-negative, so you will have a starting feasible solution consisting of a identity column, and then you can begin with your simplex algorithm, and then you will see that you will either move here or here, and then from there you will come to this point. So in 2 dimensions it was it looks so nice and simple, but of course things can become very difficult, because when dimensions are very large you cannot see the picture, but the idea, this is the idea, to show you how the simplex algorithm was thought of and how it proceeds, right? Okay. So to give you a little more insight into the geometry behind the algorithm, I'll make a few definitions now. Concept of adjacency. We say that, so a few definitions. So see, the thing is that, okay, x and y are two distinct vertices or extreme points. I'll be using vertices or extreme points synonymously. Vertices of the polyhedron P. It is understood that I am always referring to the standard LPP. So, therefore, the constraints are equality constraints and you have the corresponding polyhedron. So, x and y are two distinct vertices of the polyhedron P. We say that x and y are adjacent vertices if for any point on the line segment so I will refer to the line segment by this x comma y. So, you have two distinct vertices, you have joined them, and because the polyhedron is a convex set, remember the line will be in the set. So, the line segment x y for any point on the line segment x comma y, it can be expressed as a convex combination of x y only, x y only. This is in the context that we said that for any feasible, for a convex set and for a polyhedron, we said that any point in the polyhedron can be expressed as a convex combination of its extreme points and directions if it is unbounded, right. So, now what I am saying very specifically here is that if x and y are adjacent vertices or extreme points, then for any point on the line joining x and y, I can only express the point as a convex combination of x and y. Okay, no other direction or extreme point will play any role. It is just that this is. Another way of looking at it is, I had showed you that when you have hyperplanes and your supporting hyperplanes, we had talked about it. So, a supporting hyperplane, if you have a convex set like this, then I can have a supporting hyperplane which meets it at one point. I can have a supporting hyperplane which meets it in this. Of course, I can show you only two particular faces of a polyhedron here, but when you have higher dimensions, you have many dimensional faces. So, a supporting hyperplane will always intersect the polyhedron in a face of the polyhedron, and what that means is that the whole polyhedron will lie when it is a supporting hyperplane, the whole polyhedron lies on one side of the hyperplane, right. So, this is the idea. So, here also you can look at it this way, that to define two extreme points to be adjacent, we say that alternate definition is x and y are adjacent. So, I am not repeating all the other things, are adjacent if and only if there is a supporting hyperplane of P which meets it in the line, this is line segment x y. We remember we were also calling this as an edge. This is an edge, right. So, if the supporting hyperplane meets it in a edge, then these are adjacent and vice versa, right. Okay. And you can see very clearly that the two definitions are really equivalent, because what we are saying is, maybe I will just show you geometrically, that you have this. So, I have a supporting hyperplane here. I am saying that this is x and this is y, right. Now, all other points of the polyhedron lie on the other side of the that means, for any other if you take any z belonging to P, then if my hyperplane, if the supporting hyperplane, this is something like, let us say d transpose x, okay, d transpose x equal to some d naught. So, this is the hyperplane, Now for Z, which is on the other side of this, D transpose Z will be greater than D naught, let's say, or less. Let me just take it to be this thing, right? This is the idea, because it's on the other side. So any point lying here, because it's a convex combination of x and y, it will also satisfy this as equality, because it's on the hyperplane, on the supporting hyperplane, right? But so it cannot be expressed as a convex combination of any other 2 points of P, because for both these points this will be strict inequality greater than D naught. So how can a convex combination of two numbers which are both greater than D naught be equal to D naught? That's not possible. So the two definitions are actually the same. So I'll use both the definitions, right? And now let me also introduce the concept of adjacent basic feasible solutions. And then we want to show you that actually, again, as I in some time ago, I showed you that the concept of extreme point and basic feasible solution, the two things are the same actually. There is 1-1 correspondence, of course, in the absence of degeneracy. Now I'll show you that this concept of adjacency is also translates to the corresponding basic feasible solutions being adjacent, right? So another definition, we say that, so remember we have been using the same notation, even though some texts might use different notations for the vertex and the corresponding basic feasible solution. I have been doing the same, just because to want to make the presentation simple. So I'll say that if x and y are two basic feasible solutions of F, and remember we are calling the corresponding feasible set as F. So the polyhedron is P and the feasible set is F. So if x and y are two basic feasible solutions of F, then and Bx, By are the corresponding basis, then x and y are said to be adjacent if Bx and By differ in exactly one column. One column of A. That is, By is Bx union, let's say, Aj slash okay, we have I'll use the notation that we have been minus Br. So remember, we replace a column here and then replace it by, so the Br column goes out of the basis and Aj comes instead. So therefore the basic feasible, the basis obtained by removing one column from Bx and adding another one, that makes it adjacent adjacent basis, right? So two basic feasible solutions are said to be adjacent if one is obtained from the other by replacing one column of the basis. Okay. So then now the theorem that I want to prove to you is that for two distinct extreme points or vertices of the polyhedron P, if the two vertices are adjacent, then the corresponding basic feasible solutions are also adjacent and vice versa. So after defining adjacent basic feasible solutions and adjacent extreme points, now let me show you the correspondence between the two. So the result that we want to prove is that for two distinct extreme points, two distinct adjacent extreme points, again I don't need to use the word distinct when they are calling them adjacent, because if they are adjacent they are distinct. So two adjacent extreme points, the corresponding basis will also be adjacent. So therefore the corresponding basic feasible solutions will also be adjacent. So this is what I want to prove now. Proof is a little, I would say, difficult, but if we go slowly we can surely understand it, and then maybe you can come back to it and read it again and again to but the idea is beautiful because it's a constructive proof and it shows you again the working of the simplex algorithm. So, the theorem, and I'll put a star to it so that you know the level of difficulty is there. So, we say that for if x and y are adjacent vertices, or okay, let me use extreme points of P, then the corresponding basic feasible solutions are also adjacent and vice versa. Okay. So, two extreme points are adjacent, the corresponding basic feasible solutions are adjacent. If two basic feasible solutions are adjacent, and the corresponding the corresponding extreme points will also be adjacent, right. So, let us give you the proof. So, we start with the assumption that suppose x and y are adjacent extreme points of P, right, and suppose this, and that the corresponding bases Bx and By are not adjacent, right. That means at least two columns, that means Bx and By differ in at least two columns, because remember the adjacency concept said that Bx and By must differ only in one column, that the corresponding bases Bx and By are not adjacent, right. Okay. Now claim, and it will be clear why I am saying it, claim there exists a basic feasible solution W such that Bw is a subset of Bx union By. What we are saying is that if Bx and By are not adjacent bases, then I should be able to find a basic feasible solution W consisting of columns which are made up from the columns of Bx and By. Because remember, this number is at least m plus 2, because Bx has m columns, By has m columns, and they differ by 2 at least. So, then this has m plus 2 columns, that is what we are assuming. So, then you will be able to find m columns from here, so that the corresponding set of columns is linearly independent and the basic feasible solution, and it gives you a basic feasible solution. So, we are saying that claim. So, suppose the claim is not true. Suppose the claim is not true, then I have to contradict it. I have to show you that it can be easily contradicted. What does it mean? Suppose the claim is not true, consider the cost vector. Consider the cost vector C j is equal to 0 if Aj belongs to By, is equal to 1 if Aj belongs to Bx minus By. That means, of course, Bx and By have some columns in common, but the ones which are not there in By but are in Bx, for those the cost is 1. For all columns which are in By, the cost is 0 and is Nm otherwise, sorry, Nm otherwise. Nm otherwise, right, where m is a large number, it's a very large number. Okay. Now, with this cost vector, you can immediately see that for the feasible solution y, the cost is 0. For the feasible solution x, the cost is not 0, and for any other feasible solution which does not have the columns from bx and by, the cost is very large. Okay. So, that means that y is the unique optimal solution. Yes, y is the unique optimal solution, right? And if we say that there is no basic feasible solution W consisting of the columns here, you see that if I start my simplex algorithm for solution x from the basic feasible solution x, then if there is nothing in the neighborhood, because bx union by, the columns do not contain any other basic feasible solution. What does it mean? When I have a feasible solution, starting feasible solution x, there is some cost. Any other solution which does not have all its columns here, the cost will be very high, because remember the corresponding Cj value is Nm, where m is very large number. So, that means the simplex algorithm when started from x will not be able to reach y. But that is absurd, because the simplex algorithm will always find an optimal solution. I showed it to you. So, therefore, the claim that exists a basic feasible solution W, said that its columns are within bx and by, must hold. It is true, the claim is true, right. So, where m is a very large number. So, let me write it down. Y is a unique optimal solution, and the simplex algorithm when started from x will not be able to proceed to the unique optimal solution. Unique optimal solution, right. So, this is absurd, but this is absurd. Therefore, the claim is true. Okay. So, there is a basic feasible solution W consisting of columns from among bx union by. So, in the proof we have to also emphasize, though it has been said, but I want to emphasize it again, that W is not equal to x comma y exists. We have shown this just now, and furthermore we have also shown that W does not lie on the line segment x comma y, because the points W, x comma y are distinct extreme points, right. In the proof we have shown that from x we will go to W and then to y when we apply the simplex algorithm and begin it with from x, considering the cost function that is given to us. So, this needs to be emphasized, and then we will finally show that this is not possible, because x and y are also the bases are also the corresponding bases are also adjacent. Okay. Once I have this now what we do is, yes, I have to construct, I have to actually show you what do I have to contradict. I have to contradict the fact that x and y are not adjacent, because I am starting with the assumption that bx and by are not adjacent. So, then I will come to the contradiction to the conclusion that x and y are not adjacent, which contradicts our starting assumption. So, therefore, this is not correct. bx and by must be adjacent bases, right. So, the claim is true. So, now let us define, yeah, okay. So, let us define define z equal to half x plus y. So, now you see whatever the components here, z has either the x component is 0, then the corresponding y component is positive. So, anyway, this has the number of, if we are assuming that this is more than m plus 1, then all those components here are positive, either here or here. Z is this, and then define this and a vector D, which is Z minus W. So, define a vector D which is Z minus W. So, here you see W also has all its columns from, so that means the non-negative components of W are corresponding to the subset of columns from Bx union By, right, and Z has all components non-negative from the columns Bx union By, because it is x plus y solution, right, and here this is this. But it is possible that some component here may be this thing may be, some components of D may be negative and some will be positive, it is possible, and some may be 0, right. So, D is this. Now, if simple observations, you see that for the component of D which is negative, let us say for Dj less than 0, for less than 0, yeah, or okay. Good. Now I define two solutions. Okay, U1 as Z plus theta D and U2 as Z minus theta D, where I have to choose theta judiciously so that both these are feasible solutions. Once they are feasible solutions, you can see that when I add them and divide by 2, I will get Z. That means, if these two are both feasible, that means they are in my P, then the convex combination, I have another convex combination for this thing, for Z, because this is one convex combination for Z, and this of course is a convex combination on the edge connecting x and y. Now, I will be able to show you that there is another one. This is the whole idea, and the construction is not difficult, because you see that here the only problem, theta of course I will choose to be a positive number, and I will show you how we choose theta. Z has all components non-negative. Now, here if there is a negative component, that can create problems, because my theta should be chosen such that the corresponding component does not become negative, right. So, that means for Dj less than 0, choose theta such that it is less than or equal to, see, I want this to be greater than 0. That means, I want Zj plus theta Dj to be greater than or equal to 0. So, this should be minus Zj upon Dj, right? And Dj is negative. So, the ratio is a positive number, and this so therefore, theta should be less than or equal to minimum of minus Zj upon Dj for all Dj which are less than 0, and this number is going to be positive. So, therefore, I can choose theta to be some positive number, but satisfying these conditions, right. Similarly, for U2, you have to take care whenever a component of D is positive, then again my choice of theta should be such that the corresponding component here does not become negative. So, for Dj greater than 0, choose in the same way, choose theta to be less than or equal to minimum of, yes, in this case it will be Zj upon Dj, right, and Dj is greater than 0. So, this is what you are doing, right, and then you choose theta finally to be something which is less than or equal to, so 0 greater than theta, and minimum of, maybe I can call here this as theta 1 and this as theta 2. So, minimum of theta 1 and theta 2, or in other words, I am choosing a theta which satisfies both these inequalities. It is less than this quantity and it is less than this quantity, then I have my theta here, and then this will imply that U1 and U2 are feasible solutions, right. So, they are feasible solutions, you have another, and yeah. So, let me come back to, okay, I will go here. So, you have another representation, are both feasible, and z, which is half x plus y, is also half u1 plus u2. But this contradicts the fact, this contradicts our assumption that x and y are adjacent extreme points. Okay. So that shows you, and go through the proof again slowly to understand what we are actually doing. So this is it. Now we want to prove the other way. Okay. Yeah. So now I want to say that suppose x and y are adjacent basic feasible solutions. Now suppose x and y are adjacent basic feasible solutions, right? And yes, so we'll see this x and y are adjacent basic feasible solutions. That is by, oh, I should say this, that is by is bx union aj slash br. Okay. Now we want to show you that the corresponding extreme points are adjacent, right? So define a cost vector Cj is equal to 0 if aj belongs to bx union by, and one otherwise. Okay. So then see immediately, you can immediately see what I am driving at. What I am saying is that because the cost vector, cost components are 0 for all columns in bx union by, it means that, yes, so what it means is that the objective function value is optimal, is 0 for all points lying on x on the line segment. So this implies that all points on the line segment xy are optimal for the corresponding LPP, right? Okay, with this objective function, all points here are optimal, right? Which implies what? So if you take, consider the basis, consider the basis bx, right? So corresponding to this basis, you have the condition that Cj minus Zj are greater than or equal to 0 for all j, because x is an optimal solution, so optimality criteria must be satisfied, and therefore Cj minus Zj is greater than or equal to 0 for all j, right? And this implies that Cj minus Zj times xj summation this is greater than or equal to 0 for all x feasible, for all x for all x feasible, right? Because components of x are non-negative for any feasible x, which means that this is greater than or equal to 0. And you have your hyperplane. You see that this hyperplane, that means for all points on the line segment xy, this will be satisfied as 0, because remember the cost coefficients here are all zeros, the zj's will be zeros, and so this will be equal to 0 for all points here. But for all other points in the polyhedron, all feasible points, this will be greater than 0. So we were looking at, see for all columns in Bx union By, your Cj's are zeros and the cost coefficients are 1 otherwise, right. So, that means for all basic variables the corresponding costs are 0 and hence your Zj will be 0. Remember, Zj is computed as Cb B inverse Aj. So, since Cb's are all zeros, therefore, your Zj's will be all 0 and hence your Cj minus Zj's are Cj's for all j. But then for all basic variables, since Cj's are also 0, so then Cj minus Zj is 0 for all j, for all columns in the basic set Bx union By, and this is 1 for all j, for all Aj which are not the basic columns in either Bx or By, right. And therefore, this expression is 0 for all points on the line segment x comma y. Now, on the line segment x comma y, every point will be a convex combination of the columns. So, I have written here convex combination of columns of Bx union By, and since for all columns in Bx union By, this quantity is 0. Therefore, Cj minus Zj xj is 0 for all points on the and the xj's are 0 for points which are coefficients which are not on the line segment. So, therefore, this expression will be 0 for all points on the line segment x comma y. I hope this is clear, because see the components of points on the line segment x comma y, only those components will be non-negative or positive corresponding to the columns in Bx union By, other components will be 0, but for components for the columns which are in Bx union By, the corresponding Cj minus Zj is 0, hence this sum is 0 for all points on the line segment x comma y. And therefore, we have already shown here that the whole feasible region, because the optimality criteria is satisfied, therefore, the whole feasible region lies in this half space where Cj minus Zj xj summation, this varying from this should be 1 to n, right, greater than or equal to 0. So, this is the half space and H is a hyperplane, right, because you have this one dimensional equation satisfied by all the points here. So, this is the hyperplane. So, but this becomes a hyperplane because you see that from your working out here that this line segment is actually the intersection of the polyhedron, the feasible region polyhedron P intersection this half space, and this is a subset of this hyperplane H. Therefore, H becomes a supporting hyperplane, and by our definition x and y are therefore adjacent extreme points. We started out with x and y as the extreme points, and now because this is part of the hyperplane, supporting hyperplane, this part of the polyhedron meets this the hyperplane, this hyperplane meets the the polyhedron P in the line segment x y. Therefore, the lines the points x comma y, x and y are adjacent extreme points. This is what we wanted to show. Okay.